Hello everyone, welcome to this presentation by Aaike from Vsparticle. A very exciting method to produce nanoparticles, and we are excited to hear from him. As usual, what will happen is that Aaike will present for around 20 minutes. In that time, I will make myself disappear. After the presentation is near the end, 3 minutes before the end, I will pop my head back in to ask a few questions. And the room stays open for Q&A for an additional 10 minutes. So the stage is yours now, and on you go.
Thanks. Can you hear me clearly?
Yes, we can hear you very clearly, and your slides are on show.
That's perfect. So good afternoon, everybody. Nice to be able to give this overview of what VSP is doing to accelerate the development of new materials. That's what I will tell you in the next 20 minutes. So I split up the presentation in 3 segments. So first, the problem that our customers are facing and that we are helping them to solve. Then again, second, the solution that we are providing. So how do we accelerate this work? And the third is the applications that we are currently focusing on. So we are active in the area of value-added materials, which is a subset of advanced materials with a strategic importance for both economic growth and industrial competitiveness. And these materials are very important, and they are becoming more important every day almost, because they are solving some of the great challenges of our time. There's a very nice report made by Oxford Research that shows the importance of the materials and also shows that their market value is growing almost to €1 trillion by 2050. So some examples of value-added materials that we have seen growing in the last decade are materials for solar energy, but also for lithium-ion batteries. Those materials or those products have really seen a boost in the past decade and are a great example of value-added materials. But the inhibit problem with material development is that to bring a new value-added material to the market, to boost the performance of your product, whether you are developing a sensor, a battery, or a next generation solar cell, is a very uncertain, time-consuming, but mostly costly process. So it starts always with trial and error material development. So you design a new material, that's what you can see here, then you build it, you test it, and then you learn from it. And then probably you need to go through multiple iterations to really find the material that fits your desire. And a single design, build, test, learn cycle could already take up months, even if you have a very advanced laboratory and well-trained people. And normally we see that companies need to go through hundreds and sometimes thousands of these cycles to really find this specific material that boosts the performance of their product. So going through all those cycles, knowing that every cycle takes up months, you start to understand why it takes roughly 10 years today to really develop a new material that is enabling next generation products. Second, that if you have developed it at lab scale, there's a whole second stage, which is difficult to scale the production to high quantities. So going to high volume, but maintaining the desired 5 years before you're able to bring the product really onto the market. So all in all, it's a 15-year to sometimes even 20-year timeline to bring a new material and enable next generation products of your product. So a great example that we are witnessing, I would say lively, is QuantumScape. It's a very hot lithium-ion solid-state battery developer. Wired made a very nice report about them. And in the last 10 years, they invested up to 300 million, and they've gone through almost thousands of different design, build, test, learn cycles to develop a certain flexible ceramic material that make their battery work. So this is a great example that shows you how complex and time-consuming this problem is. After 10 years and 300 million investment, they now have something that works in lab scale, if I understand it correctly. But still, there